This is the lesson video for 12.3, which is called Law of Sines. The homework problems are here that were not available, that were covered up on your original homework key, and the homework video can go through those with you, or you can pause it here and look and see what the book's part of that was. Then in your notes notebook with a calculator, you're going to need to be going along with us and pausing the video where you need to work problems out. So in the very beginning, what I would like you guys to do is pause the video and find the area of each of these triangles. Work with your table partner, think it through, because we're trying to make a connection. So just watching the video here and just pretending that you understood the connection won't work. So please pause the video right now and come back when you're ready to check your areas. If you're back, you are checking to see that the area on this one should have been 48 square inches. On this one, we can go ahead and do the area formula that we're used to using, 1/2 a base of 12, and then because, they don't show that it's perpendicular, oops, that the height should be 8. You could actually find that with some Pythagorean theorem if you weren't sure if that was a right triangle because of the isosceles nature. On the second one, though, you don't have all that same information. You need the altitude or the height of the triangle in order to find its area by the 1/2 base times height formula that you've been using for triangles. So one way to accomplish that would be to use some of the right triangle trig, that the sine ratio from your reference angle of 66.8 degrees would be the height over that hypotenuse. So without rounding off here, the height is exactly 4.61 times the sine of 66.8 degrees. Once I have that height, then I'm ready to go use our 1/2 base times height formula and get that triangle's 9.66 for base, and get that triangle's area times the height. And you would come out approximately, and I'm rounding to the hundredths here, 20.47 square centimeters. Again, pause the video, think through what you know about that, what you understand, or what you may need to go back and spend an extra moment talking about. So we're interested in being able to get triangle areas using some of that trig information that we already have. So the triangle formula you're used to is awesome if that's the information we have. So area for a triangle that we know so far is 1/2 base times height. If the triangle happens to give us 2 of its side lengths and the angle in between, that side, 2 sides, angle in between condition that we were used to from triangle congruence, then we actually can find this letting our trig help us find the height. So we would use a sine ratio in order to find the height. If that's the condition, SAS, that we have, we'll be able to do that. And then we'll use our 1/2 base times height formula to find the area. So with this triangle, if I use a sine ratio to find height, sine from 40 degrees would be the triangle's opposite, or altitude in this case, compared to the side length, which serves as the hypotenuse of a right triangle. So we could find the height by doing 100, that hypotenuse length, one of the triangle sides that when we drop the altitude becomes a hypotenuse, times sine of 40. Then area for our triangle can be calculated, but again, I don't want to round anything off, with its other side length that we hadn't used yet that serves as its base, and then the 100 sine of 40, which is serving as its height. If you notice in our example, each of the side lengths got used, and then the sine of the angle in between those two got used as well in order to calculate the area. So there is a way to calculate area, letting some of our trig come into play. The way to do that is the area is given by a formula that we can derive from this triangle that's in that generic side angle side position. So my 2 side lengths given are A and B, and the angle given would be angle C for the angle included by those 2 sides. So again, I would use a sine ratio from my angle C in order to get my height. So the sine ratio from angle C would be compared to opposite over what becomes the hypotenuse of that right triangle. So the height of my triangle can be calculated by one of its sides times the sine of that angle. From there, I'd be able to go put that into the area formula. Area formula would say 1/2, side length serving as our base, and then what's our height for that base. And this is what's called the side angle side triangle area formula, or conjecture, because it allows us to find area from the two side lengths and the included angle by calculating the base, or calculating the height in there for us with that sine ratio, and then calculating the area of the triangle in one step instead of in two. When you go to read in your book, you're also going to read investigation number 2. And this leads us into a form of trig that we can use with any triangle. It doesn't have to be a right triangle. And what this allows us to do is take trig a little farther. Your SOHCAHTOA relationships are only good for right triangles because they are based on similarity of right triangles. We can talk about other triangles if we change our trig just a little bit. So in your reading tonight, you're going to see this diagram, but we're going to use it as a way of finding another trig relationship that holds for any triangle, not just right triangles. So in this triangle that's shown, if I asked you to get the altitude, because you have all three side lengths listed, there'd be more than one way you could set up a sine ratio and calculate the height of that triangle. For instance, I could use the sine ratio from angle A, and from that diagram, my height to hypotenuse, or opposite to hypotenuse ratio, would be that. And therefore, the height, one way I could describe the height is that it's side length B multiplied by the sine of angle A. And that's that height right here for that triangle from C. However, I could have gone over and used that angle at B and found that the sine ratio from angle B would also be helpful in calculating that height, because it would be height compared to what would be the hypotenuse on that triangle. And therefore, the height of this triangle can also be calculated from the other side as side length A times, as I miswrite that, I should say angle B. So two different ways going from two different angles to get that altitude. Well, that altitude only has one length. So in doing that, I know that B times sine of A is equal to A times sine of B. And this no longer is dependent on this being a right triangle. That altitude made right triangles, but the actual triangle ABC itself is not a right triangle. Now if I go in reverse, I can put this back into a proportion. To me, this looks like cross products. And here's what the proportion would have said. It would have said that the sine of A, and there would have been a B side length under here. And up here it could have said sine of B, and A is a side length under here. And this is going to work us into a formula right here that says for any triangle, not necessarily a right triangle, although it works for right triangles. For any triangle, I can put into ratio this sine relationship from one angle to the side across from it. So sine from angle A gets put into ratio with the side across from it. And sine from angle B can get put into ratio with the side directly across from it. And therefore, those two things have to be equal if they would each be able to be used to calculate the height of that triangle, that side, that H. The more of this you read and the more of this you look at, you'll come to see that this could be done from any of the sides of a triangle, and it doesn't have to be a right triangle. So trigonometry has several laws. This is the only one we're going to work on that lets you do trig from any triangle. The trig's a little different. So law of sines is for a triangle with angles A, B, and C. That means any triangle can apply for this. It does not mean it has to be a right triangle. And then the side lengths have to be the length opposite the angles so that we know position-wise. So whatever our angle A is, we label the side length across from it as lowercase a. Whatever our angle B is, we label the side length opposite it B. And whatever our angle C is, be it a long side or a short side, it's not a hypotenuse always, it's C, then they're saying that the sine ratio that would calculate the altitude from either of the two angles that could do it would give us this relationship saying the sine from an angle is in ratio with the side of the length across from it, or the length of the side across from it. And we could do that from any of its three angles. So it's called law of sines, because it only works with sine ratios, because those would be used to calculate the heights or altitudes from each of those angles. And this works for any triangle. So we're going to put this into practice. Up in the box, I've got some reminders. SOHCAHTOA, which is really called right triangle trig, can only be used with right triangles. Its conjecture would start if a triangle is a right triangle, then. The other two, the area formula from that side angle side condition, can be used for any triangle as long as we have two sides in the included angle. And law of sines, again, can be used with any triangle for which we have enough information to plug into it. So the things you're going to be asked to do are based off those three. So for example, in this triangle, which is not a right triangle, we can tell that from its angle measures alone, they're interested in the triangle's area. I have a side of 43, but I don't have the height from there. So this would be a good triangle to consider using some trig to solve and find the parts of. I do have two side lengths, so two side lengths, and the included angle. So I have the SAS condition, so therefore I can use that triangle area formula that says 1/2 one of the sides times the second side times sine of the angle in between those two sides. So I will have 1/2. The order of your side lengths here does not matter in this product. And then sine, and it needs to be that angle in between. So I cannot do this from the 50-degree angle in this picture because I don't have the angle on the other side of it to make it an included angle. And when you calculate, your area should come to about 570.95 square centimeters. On the next two examples, they are missing a piece of a triangle, and they are very interested in seeing if we can locate it. If these were right triangles, we'd be looking at SOHCAHTOA, but they aren't right triangles, or at least we don't know if they are. So on the first example, what I see is I have a 12-degree angle, and I am interested anyway, in the side across from it. Law of sines can be used for any triangle as long as I have 3 of the 4 pieces it requires. It requires 2 angle measurements and 2 sides across from those angle measurements, and only missing up to one of those items. So I could set up a ratio from that law of sines that says sine of 12 degrees should be able to be put into ratio with the side across from it, as long as I have one complete set of angle and side across from it in my triangle. So sine of 43 over 16. This will require some cross products. So as you work your cross products, be sure that you're showing good algebra in homework as well. So the side length that's missing is going to be 16 times the sine ratio of 12 degrees. Make sure you close parentheses on your calculator when you're calculating so it knows that that sine ratio calculation is done. Over sine of 43 from cross products, and our missing side length is around 4.9. And I'm going to say units because it wasn't listed. It does make sense that that side length is smaller than 16. In the final problem, they're missing an angle measure. And law of sines can help us with that. But it would help, we would need the side across from it, which we don't have. So that would mean we'd have 2 pieces of that proportion that are missing. So in order to do that, we aren't going to look for x. If I could find the other angle in this triangle, I could then find angle x. And since from the one I labeled y, just randomly, I do have the side across from it, 32, I could say that the sine of angle y, across from its 32 length, should be able to be put into proportion with the set I have both of, sine of 41 degrees over 24. It's the side across from it. And then I should be able to complete some work here to come up with the angle measure that I want. And then eventually to get the angle that was asked for, I'm going to need to do a little triangle sum. Take off the measure of angle y, and then I should be left with the measure of angle x. So that's my main plan. So let me go back to my law of sines setup. So I will have by cross products 24 sine of y is 32 times sine of 41. Again, notice I've put no approximate values in here. Dividing both sides, I'm going to get that sine of y is 32 sine of 41 over 24. And I could go to my calculator and get the right-hand side of that as a decimal if I'd like. But now I need to actually get the angle measure for y. So just as I would do in right triangle trig, if I have the ratio for sine, I'm going to use sine inverse of my ratio, whatever that value was in its exact form, to find my angle measure for y. It's around 61 degrees, but again, I don't want to round that off. I want to keep that full value on my screen and then go employ my plan to find that my angle measure that's missing, and please take the video or pause the video and actually check this and make sure you can do this, is around 78 degrees. Your tasks for law of sines are listed here. Please make sure your calculator's in degrees.